Welcome everyone. So today we're going to talk about harmonic oscillator in quantum mechanics. Harmonic oscillator in quantum mechanics is the quantum analog of the classical harmonic oscillator. So it is a fundamental model system in quantum mechanics where a particle is confined by a quadratic potential, which is V of x is equals to half k x square. So we are talking about this type of potential, which is like a parabola. So this system is crucial in quantum mechanics because it can be solved exactly and it can be used as a good approximation for many systems near stable equilibrium like molecular vibration. And the key features of this system is that it has quantized energy levels and its energy levels are equally spaced with non-zero minimum energy called the zero-point energy. Now we are going to calculate the wave equation for the harmonic oscillator. So here we are considering the potential energy V, which is equals to half m omega square x square. So for this potential energy, the Schrodinger equation is d2 psi dx2 plus 2m by h cut square into E minus half m omega square x square into psi. So this is our equation 1 for the wave equation for the harmonic oscillator. To simplify equation 1, we have introduced a dimensionless independent variable y. Here y is equals to beta x, where beta is root over m omega by h cut. And to put the value of y in this expression, we need to calculate d psi dx and d2 psi dx2, these values in terms of y. So we have calculated this, and putting these two values in the equation 1, we get d2 psi dy2 plus 2m by beta square h cut square minus y square into psi equals to 0. So we can simplify it further and write it as d2 psi dy2 plus lambda minus y square into psi equals to 0. Here lambda is equals to 2m by h cut omega. So now this is our final equation for the harmonic oscillator. So now we are going to consider the solution of wave equation for harmonic oscillator. Now for the equation 2, d2 psi dy2 minus y square psi equals to 0, the solution is psi equals to e to the power plus minus half y square. But this solution is not a good solution. To make this solution behave asymptotically, we substitute psi of y equals to u of y e to the power minus half y square. So putting these values of psi of y in equation 2, we get this equation, and we can see that this equation is identical with Harmite's differential equation. If we equate these values of lambda minus 1 with 2n, so when lambda minus 1 equals to 2n or lambda equals to 2n plus 1, here n can take the values 0, 1 to any non-negative integer values. So the general solution of equation 3 is psi of y equals to n hn of y e to the power minus half y square. Here this n is the normalization constant and hn of y is the Hermite polynomial of degree n. So the general solution is psi of y in hn of y e to the power minus half y square. Here hn is the Hermite polynomial and n is the normalization constant. To calculate this normalization constant, we apply the normalization condition, and by calculating this integral, we get the value of n in terms of beta. So putting this value of n in this expression, we get the normalized wave function of harmonic oscillator psi n of x in this way. And for here hn is the Hermite polynomial, so depending on the different values of n, hn can take different values, like for n equals to 0, h0 of y is 1, for n equals to 1, h is 2y. Similarly, for different values of n, hn can take different values. So from our previous discussion, we get that lambda equals to 2e by h cut omega, which is equals to 2n plus 1. So the value of total energy En is n plus half h cut omega. So depending on the values of n, En can take different values. So n can take values 0, 1 to any non-zero integer values. And for n equals to 0, E0 equals to half h cut omega. This is called the ground state energy or the 0-point energy. The energy level diagram for harmonic oscillator is this one. Here the dotted lines are the wave function and this dark line is the probability density of this wave function. So for n equals to 0, E0 is the ground state energy and its corresponding wave function is psi 0. And for E1, the wave function is psi 1 and this is the psi 1 square. the probability density. Similarly, for E2, the wave function is psi 2. So this is the energy level diagram of harmonic oscillator. So from the expression of total energy, we can see that the energy levels are quantized because En can take different values depending on the values of n, and the energy levels are also equally spaced, and it also has a non-zero finite ground state energy. These are some key features of quantum harmonic oscillator, and this was our discussion on quantum harmonic oscillator, and on our next class we will learn about the rising and lowering operators. Thank you everyone.